Hello everyone, my name is Şahin Akın. I am from Middle East Technical University, Ankara, Turkey. I'm going to present our paper, which is titled as Climate Change Impact on Multi-Objective Optimization, a case study on educational buildings. As we all know that the green gas emission level is highly increasing since the Industrial Revolution, and it continues to rise due to human activities of our time. And the green gas emissions are seen as the main contributor of global warming. When we'll just look at the sectors, building sector is responsible almost 30% of carbon emissions and has more than 30% of the total energy consumption globally. And these green gas emissions has detrimental impacts to our climate, and it increases the temperatures, which is causing the global warming. And the changing weather conditions due to global climate change is expected to have some drastic effects on the existing buildings' performances, especially its energy demand and the occupant comforts. In order to cope with these changing to our environment, the retrofitting actions and the renovation actions is quite critical to increase the existing buildings' performances. When we look at the typologies, the educational facilities are just quite critical to be spotted on because it has high occupant density, and the students are just spending most of their times during the day in these buildings. When we just look at the objectives of the existing buildings' performances, we can just see that there's a trade-off between these objectives. For example, if you would like to increase the occupant comfort during the winter time, you can just heat the building more, but it just can cause you as the increased number of digits in your bills. So in order to finding an optimal solution between these two contradicting objectives, optimization processes are seen as the key solutions for finding the best optimal solutions for between these contradicting objectives. However, these renovation activities should be also planned not only for our current weather conditions, but it should be also evaluated by just also considering the prospective weather conditions too, because our building is going to survive for future years too. In the study, we would like to propose an approach which focusing on the realization of a multi-objective optimization with the objectives focusing on reduction of discomfort hours and total energy demand for prospective retrofitting actions. And we also applied this methodology for different climate conditions, the one for the current average weather conditions, and we also use a trajected prospective weather data, and we applied the same optimization process for these two different the weather data. So in order to summarize our objectives, we would like to find optimal retrofit combinations for an existing educational building with the goal of minimizing occupant discomfort and energy use. And also we would like to propose a framework for decision makers in retrofit planning processes that allows comparing optimal retrofit combinations under different climatic conditions. In order to apply our framework, we used a case study building, and in this case, we selected our Faculty of Architecture building, which is located in Ankara, Turkey. The Ankara is in İŞERİ climate zone 4B, and it is known as it has a dry continental climate with hot summers and cold snowy winters. I selected this picture. Actually, it shows the departments and the general spaces of the building much more effectively, because right now we have a lot of trees around it. So I selected this one. The building was constructed in 1960s. It does not have any insulation in the walls or the floors, because it was just built by concerning the modernist approach. And it does not have any active mechanical ventilation or cooling system currently in the building. The building has several departments, including architecture, industrial design, city planning. And these spaces are heated from late fall to late spring using a central heating system. In order to apply several retrofitting actions for our faculty building, we defined several retrofit scenarios, which are focusing on different building components. For example, air tightness, opening ratio of exterior windows, glazing types, shading types, roof insulation, wall insulation, and window frame types. You can see the current building condition in the third column, and our prospective retrofit actions values in the fourth column. We use both the continuous variables and the discrete variables for applying our retrofitting actions into our building. And as I said before, we selected two objective functions, which are discomfort hours and the total energy demand. For the building energy simulations and optimization, we use Design Builder software. We have two different models, which were the detailed one and the simplified version of the same partial model of the faculty building. We use simplified partial model in this study in order to reduce the duration of optimization simulations. But this partial model is also representing the general layout of the faculty building. It also has the similar spaces in this one too. We use Design Builder's optimization module that implements the non-dominated sorting genetic algorithm 2, in other words, NSGA2. The population and initial random population sizes were determined as 100 individuals. Our first objective, discomfort hours, were calculated by summing up the exceeded degree differences from 28 Celsius degree. And for our second objective, we mainly focus on the heating and lighting demands only, since the building does not have any active mechanical ventilation and cooling system. For different weather data, we use, first of all, the current average weather data, and secondly, we use projected weather data. You can see in the figure 3, the blue one is the projected one. The projected one was generated using weather shift. The offset data is a climate projection generated by coupled model intercomparison project phase 5. And the projected weather data is actually represents the RCP 8.5 scenario, which is the business as usual scenario as a worst case scenario for the year of 2060. So in order to understand the differences between these two optimization results, we used a hypervolume indicator, which is based on the comparison of the two Pareto sets of the two optimization results. The method calculates the volume of the dominated region of the distribution of the objective functions. Apart from the hypervolume indicator, we used a statistical comparison of the Pareto sets in order to understand whether there is a statistically meaningful difference between these two Pareto sets. So as results, you can see that in figure 5, the optimization process with the current weather data has resulted like this. There were thousands of simulations combining all of those retrofit scenarios. and the second one was the project data optimization results. By switching back and forth between these two optimization results, you can see the differences between them. For the current weather conditions, 49 optimum results were produced. Discomfort hours varied between, for the current weather data, 1,005 and 2,321, and the total energy demand varied between 37 and 47 kilowatt hour per meter square. Discomfort hours are actually found quite high to any reference building because our building was built in 1960s and it does not have any kind of insulation in the walls or the floors. For the projected weather data, the Pareto set resulted between 1,407 hours and also 2,576 hours. And for the second objective, the results were varied between 35 to 45. So for the results, it can be understood that the project weather data contains higher dry bulb temperatures and irradiation values as compared to the current weather data. So the total energy demand values were resulted in lower compared to the project weather data. And also discomfort hours were found higher because of that reason. And also we conducted the hypervolume indicator for the comparison of these two Pareto sets.
Hello everyone. In these results, we just wanted to compare two Pareto solutions based on statistical approaches, and you can see that in table 3 and table 4, two different objectives, the results, mean values are different from each other. And by just checking for the skewness and kurtosis values, we can see that for the energy demand results, the samples, the outputs are differentiated for each other. But for the discomfort hours, they are a bit closer to each other by just distribution properties. But the mean values are higher. Mean value difference is higher than for the energy demand. You can say that, maybe. And in extra, we just apply t-test function for each Pareto solutions objective function. In table 4, you can see that the comparison, t-test comparison for the discomfort hours, we can see that there's a significant difference of average values between two Pareto sets by just checking the 30 T49 values. In extra, we can say that the current weather data optimization results were 538 discomfort hour lower than the projected one, which is directly related with the higher outside degree temperatures. For the table 5, you can see that comparison of the two different energy demand results, and we can say that they are both strongly correlated to each other by just checking the correlation parameters. It's very high, and it's similar for the first one also, for the discomfort hours also. But in the end, by just checking T49 values, there's a significant difference for their value distribution, but the distribution trend is similar for each other. In conclusion, what we try to achieve, we have tried to achieve a framework for the decision makers by just under the different climatic conditions, and by just checking table 4 and table 5, you can see that it is achieved, obviously. And in extra, we were just searching about the efficiency of the retrofit planning in terms of adding different longer term planning in the longer term. And as you can see that for the future conditions, the results are changing, distribution are changing. That means by just executing retrofit planning process, it needs to be just considering the future weather conditions. And last of all, we just wanted to obtain optimal results for each climate conditions. And by just checking figure 3 and figure 4, you can see that we had achieved that results. Thank you for listening. Have a nice day.